Good day. Welcome to another session for our mathematics live class. Now today we are going to be picking something hands-on and more calculation intensive. In fact, more calculation intensive than we have ever done so far within this Jamb series. Today we'll be looking at the concept of calculus. Now in calculus, we have to first and foremost realize that as far as calculus is concerned, there are two broad concepts between or within it that are very, very important to ensure that we have a very good grasp of calculus for this level. We have to talk about the concept of differentiation as well as the concept of integration. These concepts are reverse processes of themselves. They are mirror images of themselves. You can in fact think of them as if you are talking about the concept of indices and logarithms. Just as indices is the reverse process for what can obtain in logarithms, so also you can have integration as the reverse process of what can happen in differentiations. However, you'd find out that there are some straightforward processes that you can have for differentiations that you might not be able to have as far as integrations are concerned. In that regard, how then can you now proceed to solve questions as simply and as efficiently as possible? We are going to be looking at all of that within this series. First off, let's begin with the concept of differentiation. In plain terms, whenever we talk about the concept of differentiation, our goal is always to try to decrease the power on the indices. Yes, indices. Whenever we talk about differentiation or whenever we talk about calculus in general, we are always concerned with what happens with the power or the powers of operation. In differentiation cases, we are always looking to decrease those powers, to reduce those powers. Those are the cases we are always looking at. Of course, it doesn't now mean that the only concept you can do in calculus is all about indices. No, we can move away from algebraic functions, which are basically indices, into other kinds of functions like the trigonometric function, the exponential functions, the logarithmic functions, and so on and so forth. However, let's begin with the simplest versions, which is the algebraic functions. Let us see how we can differentiate all those differential algebraic functions and see what kind of results we would have. First off, let us consider the general form of the algebraic function. And the general form is what we refer to as y is equal to ax raised to power n. Y is equal to ax raised to power n. We can identify this a as the coefficient of this indices x raised to power n, where this x is the base of the indices and then n is the power of the indices. We have looked at these terms before. Now, in general terms, whenever we want to differentiate, we always differentiate the dependent variable with respect to the independent variable. How do we define this? We say the dependent variable is a variable that can only be determined using the values in this right-hand side, which means that in order to get what y is, we need to use the values we obtain from this ax raised to power n. It means that the value of y depends on whatever these values are. That is what it means to be a dependent variable. Another way to look at it is that the dependent variable is always that variable that has been made subject of the formula, which means that variable that is standing alone. The independent variable is the variable that is necessary in order to find that variable that has been made subject of the formula. So x in this case is an independent variable because it is standing there and the values you feed in for x will be used to find the corresponding values for y. So it means that x is the value that must be given first. Hence the reason why it is independent, because it is the starting point. And then you will now use those values to find the corresponding values for y. Hence the reason why y is dependent. This is all it means to talk about independent and dependent variables. Keep that in mind. Now, when we differentiate y with respect to x, which means we differentiate the dependent with respect to the independent variable. So we write this, the differentiation of y with respect to x, as dy over dx, or dy dx as we call it. Differentiation of y with respect to x. And how do we do this for this simple algebraic case? We take the power and use it to multiply the coefficient. So we take n multiplied by a, then we write the base, and then from this power we subtract 1. So we take the power, multiply the coefficient, then the base raised to the power of that power minus 1. So the final differential will simply be na x raised to the power of n minus 1. This is what it means to differentiate y with respect to x. This is simple level differentiation. Let's see it in examples. For instance, if we are asked to differentiate y is equal, or let's skip that, differentiate y is equal to x raised to the power 3, how would we do this? All we simply have to do is, since y is equal to x raised to the power 3, then the differential of y with respect to x will simply be take the power, multiply the coefficient, which is 1 obviously, x raised to the power of 3, then minus 1. That's all. And then we'll have this to be 3x raised to the power of 2. So take 3, multiply the coefficient, 3 times 1, x raised to the power of 3 minus 1, which will give you 2. This is how to carry out basic level differentiation of an algebraic function. You can also extend this concept. Of course, it is not compulsory that you have to take the functions one by one. You can also have a case where you have numerous functions that you want to differentiate at the same time. For example, let us differentiate x cubed plus 5x squared minus 7x plus 6. This is what we want to differentiate. How do we do this? Solution. Now, of course, you have been given the algebraic function. They are to differentiate this algebraic function with respect to x. Now, of course, you can say let y be equal to this. That's fine. But a very shorter way of doing it is differentiation of this algebraic function with respect to x. So instead of writing the y dx, where we now have to say let y be equal to all of this and say the y dx, instead of that, we can just take d dx of this algebraic function. So d dx means you are differentiating with respect to x for this algebraic function. And now what do? We pick this algebraic function piece by piece. Whenever you have these signs, which are addition or subtraction signs, know that it means that the differentiation can be taken within each of those additive processes. The differentiation is a sign that is largely associative, which means that you can differentiate this plus the differentiation of this minus the differentiation of this plus the differentiation of this. In full terms, this is what I'm saying. I am saying I can write this as d dx of x cubed plus d dx of 5x squared minus d dx of 7x plus d dx of 6, which means differentiate each of them with respect to x. Simple and straightforward. Now, how do we do this? Differentiation of x squared, x cubed. Remember, you take the power, multiply the coefficient. So you have this as 3 times 1, which is 3. X raised to the power 3 minus 1. That will give us 2. This follows the same principle as this one. For this one, remember it is plus differentiation of 5x squared. Take the power, multiply the coefficient, 2 times 5, that gives you 10. X, 2 minus 1, which gives you 1. So you can have 10x raised to the power 1, or you can just write it as 10x. Minus, differentiate this. The power here is 1. 1 times 7 is 7. They have 1 minus 1, which is 0. And then you know that when you have x raised to the power of 0, any non-zero value that is raised to the power of 0 will give you what? 1. So it means this is still the same thing as saying 7 times 1, which is still 7. And then you come here, the differentiation of 6. What would we have as our answer? Now, this is very, very beautiful. When you want to take the differentiation of 6, consider the differentiation of 6 as you taking the differentiation of 6x raised to the power 0. Of course, because when you take x raised to the power 0, it's still 1. So it still has not changed anything. However, what does this inherently mean? It means that if you differentiate this, remember the rule we have been following, you take the power multiplied by the coefficient. So it means that this will be 0 times 6. And 0 times 6 will simply give us 0. And so if you have 0 times 6 giving us 0 here, regardless of whatever is left on this side, what would you be left with? You'll be left with 0 times anything. And you know that 0 times anything will simply give us 0. As a result of that, even if we were to write this out, 6 times 0 gives us 0. X is power 0 minus 1. You'd have this as 0. X is power minus 1. But because this is 0, all of this one is useless. You have it as 0. Simple and straightforward. So that is why we can now generally say that whenever we differentiate a constant, our answer is always 0. This is the reason why whenever we differentiate a constant, our answer is always 0. Because of the fact that since it's a constant, it means that the variable here is raised to the power of 0. This is what it means whenever you hear them say that if you differentiate a constant, the result is 0. Make sure to keep that in mind. So differentiation of 6 here will simply give us 0, and then your final result will simply be 3x squared plus 10x minus 7. Simple and straightforward. This is how to solve differentiations where you have a combination of algebraic functions. You must do well to keep this in mind. However, one important note is this. Does this now mean that algebraic functions are the only kind of functions we can carry out differentiations on? The answer is no. There are numerous kinds of functions that can be differentiated. And for each of those functions, the rules in which we use to differentiate those functions differ. Let's pick a good example. If we carry out the differentiation, so we have done differentiation of algebraic functions. If we carry out the differentiation of exponential functions, how do we do this? When we talk about exponential functions, we are talking about functions that have this general form. Consider the general exponential function y is equal to e raised to the power of f of x. This is the general exponential function. Y is equal to e raised to the power of function of x. So it means that e, of course, is the reason why it's an exponential function. E is the exponent. In numerical terms, it is approximately 2.718, although the number continues infinitely in terms of the decimals. E makes it an exponential function, and then when you take the exponent of a value, that value becomes immediately the power of the exponent. So y is equal to e raised to the power of f of x, or exponent of f of x. To differentiate this, what do? The basics for this is, first off, whenever you want to differentiate this, you pick the power of the exponent and you differentiate that power. First off, you pick the power of the exponent and you differentiate that power. So, whenever you differentiate the power, that means we are going to have f prime of x. Now, f prime of x is a notation that shows us that, yes, this has been differentiated. So let's explain those notations for us. Remember, we said when you differentiate y, you get it as dy dx. I can write dy dx as y prime of x. When we say y prime of x, or we can say it as y prime, we have said this prime on top signifies that, yes, this function has been differentiated once. This function has been differentiated once. We are going to talk about higher derivatives, so you see terms like y prime prime, y prime prime prime, y raised to the power 4 in brackets. So it's telling you that it's not just an indices raised to power kind. It is telling you that this is a fourth differential. We are going to look at all these terms in terms of higher derivatives, but for now, let's stick with the first derivative. So when you see y prime, we are talking about the fact that, yes, this function has been differentiated once. When you say y prime of x, is just saying that, yes, it was differentiated once with respect to x, which is the independent variable. So when we say y is equal to this, we can also write this as y of x is equal to this, which means y, which is a function of x. So whatever y is serving us here is what f is serving us here as well. That is why we can know that whenever we differentiate f of x, we will get f prime of x. Or in another way, we would get df dx. But then writing df dx would be so big, so we can shorten this as f prime of x. I hope that makes that notation very, very clear. Now, what exactly are we going towards? If we have f prime of x, so it means that whenever you want to differentiate an exponential function, pick the power first and differentiate it. Then multiply that differential by the original function. So the differential of an exponential function is the product of the differential of the power times the exponential function itself. This is how the exponential function works. Let's take examples to see. Let us find the derivative of e raised to the power of 3x. E raised to the power of 3x. This is simply telling you that we are finding d dx of e raised to the power 3x, or if you like, you can say let y be equal to e raised to the power 3x, the same thing, just like how we did here. And then if you are finding the differential of this, the first thing you have to do is find the differential of the value of the power of the exponent. Now, if you differentiate that, that means you are taking the d dx of 3x first, which will satisfy this one, then multiplied by the exponent itself. That is all we are doing. And then the differential of 3x is simply 3. Of course, because this is x raised to the power 1, 1 times 3 is 3. 1 minus 1 gives us 0, x raised to the power 0 is 1, multiplied by e raised to the power 3x, which will give us 3 e raised to the power 3x as d dx e raised to the power 3x. Simple and straightforward. So whenever you have an exponential function, go to the power straight up and differentiate it. Differentiation of 3x is 3 times e raised to the power 3x. Finish. Process is simple and straightforward. These are processes that you can even do within your head. Exponential functions, differentiate the power, multiply the answer by the exponential function. Simple and straightforward. Let's look at another example. If y is equal to e raised to the power 5x squared plus 7x, find y prime. So y is equal to e raised to the power 5x squared plus 7x. So to find y prime, which is simply dy dx, we simply have to first and foremost take this power. So we need to find the differential of 5x squared plus 7x, then multiply that with the exponential function. And then differentiating this, 5x squared will give us 10x plus 7, all multiplied by e raised to the power of 5x squared plus 7x. Simple and straightforward. This is how to apply the differentiation of exponential functions. It is very, very important to note this. You would also notice that the moment we got into the exponential function, some of the powers, or in fact the powers we have considered so far, has been values of functions that are what? Algebraic functions. What this means is that different kind of functions can coalesce or combine to form an hybrid kind of function. So this is an exponential function with an algebraic power. It obviously now means that the power itself does not mean that all the time that power has to be algebraic. No. The power can be something, in fact, originally different. The power could be logarithmic. The power could be exponential function again. The power could be algebraic. The power could be trigonometric. What it now means is that in order to differentiate, you now must have a knowledge of the different ways in which you can differentiate each kind of function. For instance, we would obviously have a problem differentiating this function if we did not know how to differentiate algebraic functions. Because without being able to find the differential of the power, we would not be able to find the differential of the exponential function. So we were able to proceed with these solutions because we could differentiate algebraic functions, which is what we have learned so far. We are going to be looking at the different kinds of functions you can differentiate and then have ourselves a general test so that we can be sure that we can use all these concepts to find different differentiation values. You would also note that while we have done all of this in simple ways, we could have further broken down this process into a longer kind of solution. That kind of longer solution is what we refer to as chain rule or functions of functions. What chain rule or function of functions stand to do is to correctly break down each stage or each step of the process so that it is clear for anybody that is trying to read it. What we have done here is simply an application of that chain rule, even though we have still even shortened the process. Let us pick this particular second question and solve it using the chain rule in its full format. so that you can see that what we call the chain rule or the function of function is something that we normally apply unconsciously in our solutions. Consider